These two topics I had skipped because of shortage of time. Okay. In the last two lectures, we discussed about the general characteristics of photodetectors, and today we will consider photoconductors. So, there are as I indicated, there are three different important semiconductor detectors. One is the photoconductors or photoconductive, sometimes it is called photoconductive detector, and photodiodes, in which we have two important categories, that is pin photodiode, so pin diode, and avalanche photodiode, APD. So, today we will discuss about photoconductive detector or simply photoconductors. Sometimes people also call this as photoresistors, synonyms, photoresistors, and when used in visible light applications, many times we also call this as light dependent resistor, LDR, light dependent resistor. Basically, variations of the photoconductive detector. The basic principle of operation is, as the name indicates, it is based on change in conductivity, detection of the change in conductivity of a semiconductor due to incident photon flux phi, incident photon flux. So, based on the change in conductivity, and hence the name photoconductive detector or photoconductors. It is one of the simplest detectors, which is basically simply a piece of semiconductor of appropriate material and generally used in this configuration. So, you have a supply here, and here is the photoconductor. There are different designs. So, this is the photoconductor, and here is the load resistance. So, the whole thing is grounded, and here is the output. So, VO, the output taken across a load resistance, and this is the photoconductor. So, light is incident on the photoconductor, which changes the conductivity of this element, and therefore, hence the current through the device. So, the current through the device changes, and the current across the load resistance changes, and therefore, you get an output. So, this is the basic configuration of use of a photoconductor or a photoconductive detector. It is one of the simplest detectors, and it is a detector which has a gain, as we will see. So, let us see the responsivity of this detector, responsivity of the photoconductor. So, how do we go about this? So, there is a change in conductivity. Therefore, if J is the current density, through the current through the photoconductor, then J comprises of two components. One is J dark plus J photo. J dark is the current density through the photoconductor when there is no incident photon flux, and J photon or J photo, we not write photon, J photo is the current density when there is a photon flux incident. We know that J is equal to sigma into E, where, okay, let me write the flower E, because sigma E, where sigma is the conductivity, and sigma is equal to rho into, that is charge rho, charge density rho into sigma is conductivity. So, this is rho into the mobility, sigma is equal to rho into mu, and rho is equal to, rho itself is equal to, if n is the number of carriers per unit volume, then n into E is the charge density, rho is the charge density, and mu is the mobility, mu is the mobility, and n is the carrier concentration, which means number of carriers per unit volume, n is the carrier concentration. So, if n0 and p0, n0 and p0 are the carrier concentration of electrons and holes, dark carrier concentrations of electrons and holes, which means n0 and p0 are the concentrations when phi is equal to 0. If n0 and p0 are the concentrations when phi is equal to, phi is equal to 0, that is dark carrier concentrations, then we have sigma is equal to rho, which is mu 0 n0 into, this is for electrons, therefore mu E, plus p0 plus mu h into E. So, this is sigma. Sigma is equal to n0 mu 0 into this, or J dark is equal to n0 mu E plus p0 mu h for the holes into E. E is the electric field, applied electric field. So, this is the dark current density. We want to find out the total current density, because from the current density then we can determine the current. So, this is the dark current density. Similarly, if delta n is the excess carrier concentration, of electrons due to phi, incident phi, when a photon flux phi is incident on the photoconductor, it gives rise to, so here is the photoconductor. So, let me show the 3D picture. And we have applied a field here. A potential here, there is a photocurrent IP. Our interest is to determine IP due to an incident photon flux phi, and then estimate, then calculate what is the responsivity. So, the photon flux is incident here. So, this is phi, the photon flux, my objective is to estimate the responsivity, photon flux phi incident. Let me consider a dimension W here, length of the photoconductor, and this area of cross section here, area of cross section is A. If delta n is the excess carrier concentration of electrons due to phi and delta p is that of holes, excess carrier concentration of holes, which is equal to delta n. Please see that, because it is the incident photon which is creating electron hole pairs. Therefore, the excess carrier concentration delta n is equal to delta p, delta n is equal to delta p. Then J photo, I want to find out J photo, just like J dark that we have determined. So, J photo is equal to delta n into mu e plus delta p into mu h into E into P. But delta n is equal to delta p, and therefore, this is equal to mu E plus mu h, mu E plus mu h into delta n E into E. And therefore, the photocurrent, my final interest is to determine the photocurrent. Okay, let me come back to it in a minute. So, this is dark, J dark, current density when there is no photon flux. When there is an incident photon flux, this is the current density. Delta n is the excess carrier concentration, E is the charge, mu E and mu H are the mobilities, and E is the electric field. Electric field is, if you apply a volt V here and W is the width, then V by W is the electric field. All right? Okay. So, let us recall, let me write P0 mu H E. If R represents, if R is the rate of generation of carriers, rate of generation, that is excess carriers, generation of excess carriers, then R per unit volume, then R is equal to eta quantum efficiency into photon flux. Recall that if phi is the photon flux, eta is the fraction which will tell you the number of electron, the carrier flux which is generated. So, eta divided by W into A. W into A has come because per unit volume. So, R is the rate of carrier generation per unit volume, then R is equal to eta phi divided by W into A, where this is for volume. But at steady state, the rate of carrier generation will be equal to the rate of recombination, and we have already seen in an earlier lecture that R, the rate of recombination, is given by delta n divided by tau, where tau is the excess carrier recombination time, Just before electroluminescence, we had discussed, before we discussed electroluminescence, we had shown that R, rate of recombination of carriers, is equal to delta n by tau, where tau is the excess carrier recombination time, At steady state, the rate of recombination is equal to rate of generation, and therefore, let me remove this dark for a minute, for a while, J dark. So, that from these two we can write delta n is equal to R into tau, which is eta into phi divided by WA into tau. delta n is equal to this. Now, we are although the total current density comprises of J dark plus J photo, we are primarily interested in the photo generated current, that is current generated due to the incident photon flux. Ideally, we would like J dark current to be 0. If there is a finite dark current, it will contribute to the noise power and hence in lowering the signal to noise ratio. But ideally, we would like this to be 0, but our primary interest is what is J photo and hence what is the photo current generated. I have written here IP photo current, but actually this comprises of also of I dark, IP plus I dark. The total current I will actually in this case comprise of I dark, both IP plus I dark. However, our interest is to find out what is IP. So, to get IP, so delta n is equal to eta phi tau into this, and if I substitute this J photo, so J photo, that is photo generated current density, is equal to eta phi tau by WA, that is delta n into E into mu E plus mu H into E, mu E into mu H plus E into E, mu E plus mu H into E. I have substituted from this expression here. For delta n here, I have substituted from here, that is all, rest is the same. Now, A into J is the photo current IP, therefore, IP is equal to J photo into A, which is equal to, so A has gone here, eta phi tau. Now, mu E into E, what is mu E into E? If you recall, the velocity of carriers V E is equal to mu E into E and V H is equal to mu H into E. If E is the electric field and mu is the mobility, then velocity of carriers is given by this. So, mu E into E is simply V E. So, this is equal to eta into phi, I do not want to jump any steps, divided by W into E, let me keep E, into V E plus V H, V E plus V H. So, this is IP. I do not want to jump any steps so that we do not miss anything. Otherwise, you can simplify this very rapidly, very quickly. So, IP is equal to, now please see that V E by W, W is the width, V E is the velocity with which the electrons travel, and therefore, that represents time. So, W by V E is the transit time of electrons. So, transit W by V E, where shall I write? Okay, let me write here. W by V E is equal to transit time of electrons, and similarly W by V H is transit time of holes. W by V H is equal to transit time of holes. So, this is essentially nothing but 1 by T E plus 1 by T H. So, let me again not jump any steps and repeat again, phi tau divided by W, W is gone, into E into 1 over T E plus 1 over T H. Phi is incident photon flux. So, if P 0 is the optical power which is incident, then P 0 by h nu gives the photon flux. This is power, that is energy incident per unit time, and divided by energy of one photon gives you number of photons incident per unit time, that is the photon flux phi. So, this is equal to P of t divided by h c by lambda, here h c by lambda, or I can take this lambda off and I write this as into lambda. Now, phi into E, phi E here, phi E is equal to P opt divided by H C by E into lambda. If you substitute C in micrometers, lambda should be substituted in micrometers, then this number is 1.24. We have done many times this one. So, this is equal to P opt divided by 1.24. You can substitute constant 6.6 into 10 power minus 34. This is in microns, therefore, it is 3 into 10 power 14 now, that 3 into 10 power 8 meters or 3 into 10 power 14, and this is 1.6 into 10 power minus 19 will give you simply 1.24. 1.24 into lambda, lambda to be remembered that this is to be substituted in microns. So, phi into E, phi into E is this. So, I want to substitute for phi into E this one. So, here. So, this is, let me remove these, now we do not need this. So, phi into E is this one. This term I want to call 1 over T, which is 1 over T E plus 1 over T H, and therefore, we can write I P is equal to eta into tau, eta into tau divided by T here, this 1 by T, tau by T into lambda divided by 1.24 into P opt, lambda divided by 1.24 into P opt. You know why I have written like this is my final interest, there it is, my expression for responsivity is equal to I P divided by P optical power incident, which is equal to eta into lambda divided by 1.24 into tau divided by T. Responsivity I P by P opt. So, the units are amperes per watt. So, I have from basic relations, basic concepts, we have derived a simple expression for the responsivity of a photoconductor, responsivity of a photoconductor. It is not a difficult derivation at all, it is a very simple one. Without jumping any steps, I have shown you that we get an expression for the responsivity of the photoconductor, responsivity of the photoconductor. R is equal to, when we discuss the general characteristics a couple of lectures before, when we discussed the general characteristics of detectors, we had an expression for responsivity R, which was equal to eta into lambda divided by 1.24. Hope you recall the graphs that we had plotted. If eta was not changing, eta was constant, then we drew this. So, responsivity R versus lambda for different values of eta, eta equal to 1, eta equal to 0.6, eta equal to 0.2. And then we, in the following lecture, we discussed the dependence of eta on wavelength, and then we got responses like this. Because eta, there was a long wavelength cutoff, and also it was decreasing down to 0 near short wavelengths. Now, we see that there is an additional term tau by T. In all these considerations, we did not take transit time of carriers into account. Now, we in this analysis, we have taken the transit time W divided by VE. So, because of the transit time, now we have a factor tau is by T. Tau is the carrier recombination time, tau is carrier recombination time. Typically, this could be from few picosecond to few millisecond. Depending on the material and the structure, design, it could be few picosecond to few millisecond, which means of the order of 10 power minus 12 seconds to 10 power minus 3 seconds. tau, carrier recombination time. The transit time t, okay, let us look at 1 over t here. 1 over t is equal to 1 over t e plus 1 over t h. In general, V e is much greater than V h because mobility mu e is much greater than mu h. In detectors like gallium arsenide or indium arsenide, if you take indium arsenide, it is mu e is about 33,000, whereas mu h is few hundred. So, you can see that mu e is much greater than mu h in general, but there are many materials where even mu e could be less than mu h, but most of the detector materials which we use, they have mu e much greater than mu h or at least greater than. Therefore, V e is greater than V h, and therefore, T e is much smaller compared to T h. Therefore, 1 by T e is much greater compared to 1 by T h. In other words, we can write that 1 over T is approximately equal to 1 over T. Because T h is much larger compared to T e, transit time of holes, that this 1 over T h becomes much smaller compared to 1 over T e, and therefore, 1 over T is approximately equal to 1 over T. We could retain 1 over T itself, there is no problem, but if we take this, then we need to discuss about the transit time of electrons only, otherwise it does not matter, there is no. So, T e, transit time of electrons, is equal to W divided by V e, and W, if I take typically W is equal to, let us say, 1 millimeter, the width here is about 1 millimeter or few millimeters, the semiconductor material, the dimension of the semiconductor. If and V e, if I apply an electric field so that V e is approaching saturation velocity, we discussed about saturation velocity, which is of the order of 10 to the power of 7 centimeters per second, then this will be nearly equal to 10 power minus 8 seconds. The transit time of electrons is approximately 10 power minus 8 per second. We are putting some numbers to get a feel for what kind of factor. If this factor is greater than 1, it means responsivity has a gain. There is a gain factor, and indeed photoconductors provide gain because of this. Now, if I use 10 power minus 8, then we can have gain means tau divided by T. So, if you go to this end, it is 10 power minus 12 divided by 10 power minus 8, which is 10 power minus 4. So, tau, this is ranging from 10 power minus 4 to, if you come to this end, it is 10 power 5. This factor is as high as 10 power 5. So, you see that in photoconductors there is a gain possible. The responsivity can be very high. I will show you a typical plot, and the number for responsivity is 10 power 2, 10 power 3, 10 power 4, very high responsivity. That is because of this. Of course, high responsivity or high gain comes at a cost. You will see that the speed is going to be much less compared to pin diodes, but there is a gain which is available in this. How does this gain come? We know about gain coming from avalanche multiplication. Like in APDs, there is carrier multiplication taking place, that is an accelerated electron knocking out more electrons, and hence there is avalanche multiplication. There is no avalanche multiplication in this case, in the case of photoconductors, but there is gain, and the gain could be very significant. So, you could have this factor tau by tau in this range. So, if you make the transit time T e, if the carrier recombination time is very small, then it could be here. Otherwise, you can have a large gain possible. Now, how does this gain come? Let us briefly discuss the physical origin of this. Where is the gain coming? Typically, the photoconductor is typically like this. They normally use a metal contact here, let us say metal, and therefore, for ohmic contact you normally use N plus here and then an intrinsic medium and N plus. It is only for contact sake. This is metal. So, this is N plus and intrinsic. So, the carriers are, the photon flux is incident here. There are better designs, but I am just explaining that there is. So, if you draw the band diagram of this, so you have N plus, which means the electron Fermi level is here, and then this is the intrinsic region, and then we have N plus. What I have drawn is the familiar energy band diagram of this. So, this is the I region, intrinsic. So, I have applied positive to this end, therefore, the potential here is decreased. So, what is plotted is E versus the distance. So, E versus the distance. Incident photon, let us say one photon is incident here to this region H. So, it creates a hole and an electron in the conduction band and hole in the valence band. The hole starts moving up, it is like air bubble, so starts moving up the slope, and this is like water droplet, so it starts going down. These are the two ends where it is collected. Now, because the velocity of electrons is very high compared to this, electron goes rapidly and reaches this end. When electron reaches this end, so when electron is moving this side and hole is moving this side, there is a current in the external circuit. There is a current I here in the external circuit because of charge carriers moving. We have discussed this in the last class before impulse response. By Ramos theorem, it tells you that there is a current which is in the external circuit. When the electron is collected here, then to maintain charge neutrality, the second electron is released from here, from this contact, because there is only one hole which is moving. Hole is still, before the hole has come here, the electron has been collected. So, a second electron is released, because this is, once it is collected, it is gone into the conductor. So, this electron again starts going down, hole is further proceeding and it is collected here, next electron is released. This is further proceeding. So, till either the electron hole recombine in the medium or both electrons and hole are collected by the contact electrode at the ends, this process takes place. Please see, there was only one photon which was incident, there is a carrier pair which was generated, but there were so many electrons were transiting through this, by the time one hole was travelling up. And this is why there is a persistent current in the external circuit for a long time, although you had just put one photon which has made one carrier. So, the current flows for a longer period in the external circuit, and that is responsive. We have discussed with one photon. If you have large number of photons, you can imagine that there is a big current in the external circuit, although there was just a burst. So, this is responsible for this, and that comes because of a large carrier recombination time, which means these electron and hole are not recombining inside the semiconductor for a long time. The moment they recombine, if this was very small, for example, this is smaller than this, then even before it reaches here, it would have recombined, which means the current will persist only for a small duration. And therefore, it is the carrier recombination time which will, but we know that because it takes a long time to go here, the impulse response will be spread even. So, now the impulse response would look like, so it is continuously coming for a long time. So, this is time t and this is current I of t for a long time, because the carrier recombination time is very large. So, what have we compromised? The speed. To get gain, what you have compromised is speed, because the impulse response is now spread, the transit time spread is much larger. So, photoconductors can provide gain, but at the cost of speed. You can indeed show that the gain bandwidth product remains a constant. Now, let us come to materials which are used. So long I did not discuss about materials. So, materials generally photoconductors are used to these are used to detect long wavelength materials, and therefore, there are two kinds of materials which are used. They are intrinsic and extrinsic. Intrinsic and extrinsic. As you know, intrinsic normally refer to pure semiconductors, and extrinsic refers to doped semiconductors. And the same thing is true here, that we have intrinsic semiconductors such as widely used semiconductors, for example, are indium arsenide and indium antimonide. This has a band gap Eg of 0.36 eV, and this is 0.17 indium antimonide. These two materials are widely used because, as I also mentioned, they have very large mobility. Electron mobility in indium arsenide is about 33,000 centimeter square per volt second, mu. Similarly, in indium antimonide, it is about 8,000 or 8,500 centimeter square per volt second. Very large mobility, and therefore very small TE, and therefore you can get relatively large gain. And extrinsic semiconductors, the widely used semiconductor is germanium doped, mercury doped germanium or copper doped germanium. Typically, the activation energy, here we are referring to this. So, let me draw this. What we are showing is, this is germanium, band gap of germanium Ge. Eg is approximately 0.66 eV, and because of mercury doping, there is a activation energy here. There is an acceptor level. So, this is the mercury level Hg dopant, and this activation energy, the energy gap here is approximately Ea is approximately 0.09 and for copper it is even smaller, I think about 0.04. So, for this it is approximately 0.04 eV, and here it is 0.09 eV. So, obviously, if you want to use these detectors, they have to be cooled, otherwise thermal agitation at room temperature, the acceptor atoms will all accept electrons there, and there will be plenty of holes here, and therefore, the dark current will be very large. So, usually you should cool these detectors at 77 K. Normally, these are cooled at liquid nitrogen temperature while using. So, the incident photon energy, if it corresponds to this activation energy, then it will respond, in the sense an electron will go here to the acceptor level, leaving behind a hole, and the hole will cause conduct. So, the conductivity is due to holes created here, just like in a p type material you have acceptor levels which accept. So, the widely used extrinsic materials are germanium doped mercury, and people also use for infrared application a material which is also widely used is mercury cadmium telluride, Hg cadmium telluride. So, it is HgX 1 minus X telluride. Cadmium telluride, so this is mainly for IR applications. Although cadmium telluride, because this is mercury cadmium telluride is lattice matched to cadmium telluride. So, you can grow different combinations of Hg cadmium telluride on cadmium telluride, and cadmium telluride has a band gap of about 2.5 eV, which is very much in the visible, but mercury telluride has a band gap which is very close to 0. So, you can by varying x, you can cover the entire IR range from visible to IR. It is possible because this is an important material which is used for IR applications, a ternary compound mercury cadmium telluride and cadmium telluride. So, if I plot typical responsivity curves for these, it looks like this. So, let me plot the responsivity. So, responsivity amperes per watt. So, typically 10 to the power of 2, 10 power 3, 10 power 4, and wavelengths are of course large. You can calculate, for example, for this 0.36 eV, what is the 0.36 eV, so which means 1.24 Eg. So, lambda cutoff, so lambda c is equal to 1.24 divided by 0.36. How much is that? Approximately 3, approximately 3 micrometers. So, lambda cutoff in, so approximately 3 micrometers, and similarly if you go for this it will be about, so let me plot, so 2, 5, 10, 15, so 2, 5, this is lambda in micrometers. So, the responsivity typically looks like this. So, this is for indium arsenide, this is for indium antimonide, and this one I have plotted for Hg germanium doped H, the other way to be written germanium. So, typical responsivity, you can see initially the linear behavior because it is proportional to lambda. If you recall, the responsivity for R is equal to eta into lambda divided by 1.24 into tau divided by T. Why indium arsenide has a very high responsivity? You can see its mobility is very high. Therefore, this T is very small. So, that is why the responsivity is very high. When we see for normal PIN photodiodes, you will see that the responsivity is 0.5, 1, 1.2, that is the kind of numbers, but here we have very large numbers. So, indium arsenide, because it has a very large mobility, has a very high responsivity. The only thing is these are much slower detectors, one, and I will come to the second disadvantage also. So, initial portion you can see this linear variation is primarily because of this linear dependence on wavelength, and then this drop we know because of long wavelength cutoff, because the band gap of the material. So, further long wavelength, the band gap of the material is larger than the photon energy, and therefore, there is no absorption, no carrier generation. Is this all right? So, we come to finally one high speed design which is widely used with photoconductors. One of the, as we discussed, one of the major problem is carrier transit time and recombination time. So, recombination time can be minimized, can be reduced by using pure materials with minimum defects. And transit time can be minimized by using interdigitated transducers. So, the normal design where these photoconductors are used, they use IDEs, interdigitated electrodes. So, let me show you. So, this is the photoconductor, and this is grown a film of photoconductor grown on an insulator, typically insulator, usually glass, transparent glass, and this is the photoconductor. This layer is the semiconductor, and on this they make IDTEs, that is interdigitated electrodes. So, let me show you. Okay, let me draw it. It will become clear as soon as I finish the drawing. These are monolithic electrodes. What I have drawn here is metal electrode which are deposited on top by lithography . So, this electrode here, for example, is connected to a supply, and this is the other electrode which is grounded. So, there is an electric field between this finger like structure. So, it is interdigitated, they are called interdigitated electrodes, IDEs, interdigitated electrodes. Interdigitated electrodes. The advantage is that this reduces the transit time. So, photons are incident here, that is light is incident. The advantage is the generated carriers will find an electrode very close. It does not have to travel, as I had shown the diagram earlier, that photons incident, the electrons and holes have to travel a long distance. So, this increases the transit time. So, to minimize the transit time and hence to increase the speed, one uses IDEs. The second advantage is, if you apply an electric field at the end, to get an E, please remember, to have a high saturation velocity VE, we need fields, electric fields of the order of 10 to the power of 4 to 10 to the power of 5 volt per centimeter. We want to have high speed, so VE should be saturation velocity, as discussed in the last lecture. You need very high electric field. If this separation is large, let us say several millimeters, then the field required will also be, the voltage required, the V to be applied is also very large. But here they are close by. the separation is very small. So, even by applying very small voltages like the TTL logic plus 5 volt, you can get very large electric field between them, because the separation is small. That is the advantage of using IDEs in all high speed devices. These are also widely used in SAW devices, surface acoustic wave devices, where IDEs are used to increase the speed. So, high speed design. One last point before we come, the IV characteristics of the photodetector. So, in all, for the design engineer, the IV characteristic is very important. One is the responsivity. Whenever you want to use a photodetector or a source, you have to know the responsivity, and second is the IV characteristics. So, how do you think the IV characteristic would look like? IV characteristic. It is a simple piece of semiconductor and you have applied a current. So, the IV characteristic of a photoconductor looks like this. So, this is what I have shown by dashed line is when, okay, let me draw it completely. So, what I am plotting is the I, the photocurrent IP versus the applied voltage V. So, you have so this is with the phi equal to 0. So, phi is equal to phi 1 and phi is equal to phi 2, which is greater than phi 1, the incident photon flux. But what you see is it is symmetric because it is simply a piece of semiconductor. It does not matter whether you apply from this side or that side, it is not a diode, and therefore, there are no rectifying behavior. So, it is simply the same. The current here is in milliamperes, including the dark current. Please see the dark current, I dark, is also of the order of milliamperes. Whereas, in the case of a photodiode, there is a reverse biased photodiode, the dark current is of the order of microamperes. So, the major disadvantage of photoconductors is the dark current, large dark current. This is a major disadvantage of photoconductors. In any high speed application or where you need a very good signal to noise ratio. But the real advantage of photoconductors is if you want to detect long wavelengths, IR wavelengths for example, then photoconductors are the detectors which are used. So, this is the IV characteristic with one disadvantage is high dark. So, what we have shown is for different photon fluxes, you can see initially it varies linearly because you are applying velocities, so voltage, and therefore, the electric field is increasing, but once the saturation velocity has reached, there is no more change in current, because current is proportional to the mobility into the total number of carriers that you have, and therefore, as electric field increases, the velocity increases. Therefore, initially it is behaving linearly, but afterwards, as you know that one reaches saturation velocity. So, this is electric field E versus velocity V. So, this is the saturation velocity, and therefore, there are no more carriers which are remaining to be swept. So, there is a average velocity where it has saturated, and therefore, the current saturates to that value. So, I think there we have covered almost all aspects which are relevant to photoconductors. One type of detector which is used for common applications, but normally not used for high speed applications, all high speed applications we use either pin diodes or APDs. The highest speed, there are various designs of pin diodes, and the highest speed that we now have, there are detectors which can detect hundreds of gigahertz bandwidth, and they are based on pin detectors, pin diodes or their variants. So, we will stop here. Is there any specific question? Any specific question? So, we will stop here.